Alright, so in this video, I'm gonna be explaining another important article on geometric deep learning with the title FILTRA Rethinking Steerable CNN by Filter Transform. So if you want to have many filters like this one and then rotate it, this one, rotate another rotation, for example 30 degree, then 60, then 90, you should cover many filters. But if you design your filter in such a way that it has some symmetric properties like this one, like star, then you save many filters, and it has even better expressive power. But you can think of these filters as bases, like bases of Fourier transform. So this paper in 2021 is very important. Steerable CNN imposes the prior knowledge of transformation invariance or equivariance in the network architecture to enhance the network robustness and geometry transformation of data and reduce overfitting. It has been an intuitive and widely used technique to construct a steerable filter by augmenting a filter with its transform copies in the past decades, which is named as filter transform. Recently, the problem of steerable CNN has been studied from aspect of group representation theory, which reveals the function space structure of a steerable kernel function. However, it is not yet clear on how this theory is related to the filter transform technique. So we show that kernel constructed by filter transform can also be interpreted in the group representation theory. Beyond the well-known property of equivalence under translation, there has been substantial recent interest in CNN architecture that are equivariant with respect to other transformation groups, reflection, rotation. Applications of such architectures range over scenarios where object orientation might vary, including OCR, aerial image processing, 3D point cloud processing, medical image processing. For example, PointNet architecture solves this problem of 3D point cloud processing. So we make use several numpy, scipy, like for example circulant is just the different ways to work on the matrices. We recapitulate the basic concept of steerable. So you know that a vector field F follows this rule when act pi of g of a group element G. Where rho is group representation related to vector field F. And this figure shows that an example of different types of representation rho for RGB images and gradient images under rotation transform. So you see examples of images with different group representations. So in the scenario of convolutional neural network, a convolutional operator, this is convolutional operator. If you convolve and then rotate, it's like rotate and then convolve. So they have a different group representation. When we say group representation, it means a map from your graph to the general linear graph group of n. For example, n by n matrices, and this such that this satisfies for any two elements inside a group. So the trivial, there are three different kinds of linear representation: trivial representation, regular representation, and irreducible representation. We write irrep to say it is irreducible. The trivial representation is always 1. So the regular representation of a finite group acts on a vector space by permuting its axes. For example, you have some feature map. So for different kernels, you have different feature maps. And then when you permute it, it means that you go to a different angle, because it is already pre-computed. The filters is applied to the image and it has become feature map. It has already pre-computed. And so we can always write the sum product, but it is up to Q. It's just change of basis. That's why we say QA, Q minus 1. And so a representation is irreducible if no non-trivial decomposition exists. And I here is index set specifying irreducible representations. Then we have this filter transform. So we have different filters, like in CNN we have different filters, but our filters are designed very smartly. They have some relation to each other. For example, if this is a filter, then the next one is 30 degree. Then the next one is 60 degree. So it is rotating. So there is a permutation. For example, when we say 60 degree, we just permute 2 times to get this. That's why we are represented with that group. So this is the regular, we decompose into regular representations. We try to make it like a left invariant or permutation related to permutation group. And the red light, yellow and green denotes negative and positive matrix values respectively. So each column in V and on W, each column corresponds to a discrete cosine transform basis. Now this is the harmonic filters. First we say a lemma that the map is equivariant if and only if it satisfies like this. So such filters, this author proved that it can be denoted by a series of harmonic bases. Harmonic bases, like in harmonic analysis, we work on bases like Fourier bases, wavelet bases, and if you just a linear combination of them, it's a combination of them, so that's more explainable, and it reduces the number of filters that you need to use. If you don't use these bases, you need to write many filters. And so consider the rotating filter K. The output of convolution with kernel K naturally permutes the input as the input rotates in Cn. This intuitively corresponds to property of a steerable filter transforming from trivial representation to regular representation. So you see the visualization of FILTRA filter examples. Based on the same weight kernel K, we generate filters.